Now that we have learned how to graphically display the relationship among two variables, it's time to learn about the statistics we can use to measure the strength of that relationship. There are two primary statistics, covariance and correlation. Covariance is a statistic to measure the relationship of the variability of two variables. When greater values of one variable correspond to greater values of the second variable, and likewise the smaller values of the two variables correspond to each other, covariance is positive. If greater values of one variable correspond to smaller values of the second variable, the covariance is negative. Here's a scatter plot illustrating a positive relationship among two variables. The unit of analysis is an automobile. If we look at all the units in this picture, we notice that the automobiles with larger engines are also the ones with more power. This is reflected by the upward trend from left to right on the scatter plot and will also be reflected in a positive covariance. Here's the formula for covariance. It may look scary, but we can simplify it by breaking it into pieces. Look at the numerator. This part of the formula is just the deviation score for a unit on one of the variables. This part of the formula is just the deviation score for a unit on the other variable. We calculate the deviation scores on both variables and then multiply them together. When we multiply a calculation for two different variables, we call that a cross product. The term product means we are multiplying, and cross simply means that we are crossing across a couple variables. We calculate the deviation cross products for all the units, then average these by adding them up and dividing by the degrees of freedom. We don't have to do this by hand. We can use R. I'm going to load the MT cars data set and then calculate the covariance of engine displacement and horsepower. It's very simple. We use the function COV, which is short for covariance, and then use the two variables as the parameters. The covariance is 6,721. The positive relationship that we see among engine displacement and horsepower in the scatter plot has this accompanying statistic, a covariance of 6,721. Here's a scatter plot with a negative relationship. Let's calculate the covariance of displacement and gas mileage. It is negative 633. We should not be surprised that we obtain a negative covariance because the scatter plot clearly shows a negative relationship. Now, what do covariances like 6721 and negative 633 tell us, aside from being positive and negative? How do they convey the strength of the relationship among the variables? I have no idea. The covariance numbers that we calculated mean nothing to me. In fact, think about the strange units of measurement. To calculate covariance of engine displacement and gas mileage, we had to calculate displacement deviations and gas mileage deviations, and then multiply these together. This would leave us a unit of measurement of cubic inches miles per gallon. What is that? Here's where correlation comes to the rescue. Correlation is a statistic to measure the linear relationship of the variability of two variables. Before we go further, I had better tell you what we mean when we say linear relationship. We've already looked at a couple examples. Here's one. A linear relationship is one in which the points on the scatter plot follow the same trend as a line that slopes downward, as it is here, for a negative relationship, or slopes upward for a positive relationship. To clarify the concept further, let's contrast this with a nonlinear or curvilinear relationship. There's a definite relationship apparent in this scatter plot among the variables anxiety and performance. This relationship helps us to understand how these variables interact. If anxiety is very low, a sort of no worries state of mind, or if it is very high, high anxiety, then we expect performance to be low. There's a balance between low and high anxiety that yields high performance. There's a relationship among these two variables, but it is not linear. Correlation would not do a good job of indicating the strength of relationship among these two variables. Let's look at how correlation does help us measure the strength of linear relationships. Correlation is standardized covariance. You may recall when we learned about z-scores that these are just standardized deviations, obtained by dividing the deviation by the standard deviation. Correlation is standardized covariance. It ranges from -1, which would indicate a perfect linear negative relationship, to +1, which would indicate a perfect linear positive relationship. A correlation of 0 indicates no linear relationship. Let's look at a formula for correlation. In the numerator of this ratio, we see covariance. To standardize the covariance, we divide by the standard deviation. Now remember that covariance was created with both variables, so we need to divide by the standard deviation of both variables. It turns out that the maximum value that covariance can have is the product of the two standard deviations of the two variables. Therefore, if we divide by the product of those two standard deviations, the correlation has a maximum value of 1 and a minimum value of -1. Now this makes it much easier to understand the strength of a relationship because we have a scale. The scale stays the same no matter what two variables we are studying, and there is no unit of measurement because the units of measurement cancel each other out in the formula. Let's look at the correlation formula a different way. Here I have put the definition of covariance in place of the symbol for covariance. What if we were to divide the deviation score for the x variable by the standard deviation of the x variable, and divide the deviation score for the y variable by the standard deviation of the y variable? Wouldn't that give us a z-score for x and a z-score for y? Then all we have left is the division by the degrees of freedom, n-1. That is indeed an alternate formula for correlation. We take the cross product of z-scores for each unit, then add them up for all units, and average by dividing by the degrees of freedom. Again, we are saved from doing these calculations thanks to our friend R. If I want to calculate the correlation of engine displacement and horsepower, I use the function cor, short for correlation, and use the two variables, displacement and horsepower, as the parameters. This gives me a correlation of 0.79. The relationship of engine displacement and horsepower that we see in this scatter plot has a correlation of 0.79, indicating a strong relationship, because remember, the maximum the correlation can be is 1. Let's calculate the correlation for engine displacement and gas mileage. It is -0.85. The relationship of engine displacement and gas mileage is even stronger than the relationship of engine displacement and horsepower, except the relationship is in the negative direction. What would a perfect linear relationship look like? It would look like this. When we measure every unit on the two variables and place them in a scatter plot, they would all fit perfectly on a straight line. The line could be sloping upward for a positive relationship or downward for a negative relationship. What about no relationship? That would look like this. It would look as though someone randomly scattered points across the scatter plot. There's no pattern. The correlation is 0, indicating no relationship. Although covariation is used for some advanced statistical methods, for basic statistical analysis, it is correlation that we use as a measure of the strength of a relationship among two variables. Now we have a graphical presentation of this relationship in a scatter plot and a statistic, correlation, to indicate the strength of relationship. These two will go hand in hand when we want to study and report on a bivariate quantitative relationship.